Okay, we continue from our last class, okay, on the fly wheeling diode, okay. Okay, so these are the examples, okay, I'm going to show you today. All right, so now we can see that it's the same circuit I showed in the slide, okay, where the moment I power off. You see, initially the power is on, okay. So the inductor here will actually charge up the energy in the form of magnetic field. Now the moment I turn off, okay, so what happened is that you will see that there will be a very high negative voltage, okay, that is actually generated by the inductor. So this inductor can be motor. The moment you turn off the motor, that is what happened. You see, motor itself can be a generator already, right? So it will not just generate the equal voltage, but multiple, okay, of the voltage. As we can see here, if we look at the unit here, right, it's actually very, very high. If we can zoom in, okay, so you can see it go down all the way to the negative 2.5. It's actually multiplied by 10 power of 4. 401, 2, 3, 4, 25 kV. Okay, it will generate that high amount. You see, my voltage is only 12 volt, but the inductor, right, will generate this spike at a very short moment of time. Like I said, it will not immediately damage, okay, your circuit, but you continuing doing that, okay, for many times, that it will cause damage, okay, to the controller. Now, if we zoom further in here on top here, you can see here is negative 500 volt already. All right. So that is what happened when you don't have the freewheeling diode. So if I zoom in here, you can see here is the 12 volt. Okay, I further zoom in. Okay, see, this is the 12 volt here. All right. The 12 volt here, and it will go all the way down the moment you turn off. So to solve this problem, like I said, you need to put a diode. Now the diode is off because I put a 0 here. So now what I'm going to do is that I'm going to change to 1. Okay, change to 1 means that this switch is turned on. Okay, so that means the diode now is connected in parallel, okay, with the inductor here. So I run the simulation again. And we look at the voltage across the inductor. See, no more negative 500 or how many watt. Okay, so this freewheeling diode will actually help discharging, okay, those induced voltage from the inductor. All right, so it's like I said, mentioned before, it is very important, okay, especially those who involve in mechatronics controlling motors. And like I said, when you use a controller chip, look carefully, okay? If you are not sure the chip you are using whether got built-in diode or not, then you put a external diode. Even with the built-in diode, right, you have to check your motor rating or current rating. Okay, if your motor current rating is 3 amp, the built-in diode won't be able to sustain. The built-in, if I'm not, what we call, if I remember clearly, it should be less than 1 amp only because it was designed for small motor, not for big motor. So in that case, you need to apply what I teach you all earlier. You need again to put external diode, which will be connect in parallel, right? So you increase the diode capacity. So again, okay, this is the inductor. Okay, the inductor is the, you change the inductor, of course, you will also what we call this change the magnitude. Okay, let's say I change increase to 1 Henry. 1000 millihenry is 1 Henry, right? Okay, put back, turn off. Okay, you will see the negative come back again. Okay, the negative will come back again. Let me just do full screen. Okay, again, it will go very, very high voltage. All right. So these are just one of the other than rectification application of a diode. Okay, because if I'm not mistaken, what you all learn diode in the analog is all rectifier only, right? That's all. They don't tell you anything already. In fact, diode have a lot more application. Okay, so one of them is this. Because power electronic, we deal with controlling motor. Okay, we deal with controlling machinery. All right, so this application, that's why after that, I think I better put here to actually, to show you guys. Then of course this, what we call this Simulink. Okay, I just do it a demo for you all. If you want to make this thing more clear, okay, you can just remove this, remove this. Okay, then you connect a physical diode. So that now the diode is physically connect, right? So you run again. Then you can see that. Okay, if I zoom in, okay, beautiful, no negative. Okay, no negative voltage. That's why simulation is very important to test out your ideas. Okay, now I remove the diode. Okay, the negative come back. Very clear differences. Okay, remember anything with inductor, not just motor, especially these what we call inductor types of cookers, right? So yeah, induction cooker, yeah. So anything got coin inside, okay, then you have to be careful, all right, on this issue. Okay. Okay, back to the slide. You don't need this one. I think you all don't need to do it here in the class. You can do it at home if you want to try. Okay, I explained the phenomenon already. Okay, so that will be all for diode. Okay, for power electronics. So now we move on to the transistor. Okay, we move on to the next component, transistor. Again, okay, sometime in this power electronic community, they always refer it as switching device. Okay, sometimes they don't use transistor. The common word is said, oh, wow, how many switching device you have in your converter? So that means they are asking you how many transistors are there. Now, switching device is a more general term because it can be MOSFET, it can be IGBT. Okay, so this is the common term used in the power electronic community. Now, transistor or switching device, okay, even I don't use the word transistor very often. I will either use MOSFET or IGBT, okay? So that is much more specific because these are the two types of semiconductor or this switching device that use in this power converter. And it is made, okay, obviously by silicon, okay? And then nowadays, there are another new types of material, okay, emerging, okay, in the industry. So one of them is the silicon carbide, so it's SiC. Okay, so the other one is this one forget already, gallium nitrate lah. Okay, so in short we call it GaN, G-A-N. So these are the two, okay, what we call new material that is slowly going to replace, okay, the MOSFET and IGBT. Maybe in another 10 years, I'm not sure, or then we no longer use silicon for this switching converter. But nowadays, like I say, it's still very expensive. Okay, the advantage is that it can withstand a higher voltage. So you no need to have serial or parallel, so many of them. Okay, so one of the transistor can, let's say, handle like 10,000 volt. Now we need to have 10 connect in series or parallel. Okay. And another type, of course, this is what you all learn in analog BJT. Okay, the NPN and PNP transistor. Okay, this type of transistor are not commonly used in power converter. All right, simply because it's not as efficient as MOSFET and IGBT. All right, because BJT is a current control device. You need to apply current to the base. Okay, so when there are current flow through, means that there are power dissipation. Okay, or power losses as well. So using MOSFET, right, is a voltage control device. So it does not have any current, okay, flow into the gate, to the drain, okay, or to the source. So it is much more better, okay, compared to BJT. That's why in the power electronic industry, so the MOSFET, okay, and IGBT will be a common switching device. Okay, here I already explained the main difference. BJT is current control, all right, and then MOSFET, okay, or this IGBT is voltage control, all right. So the difference is that BJT can actually handle higher current compared to MOSFET. And then MOSFET can handle higher switching frequency compared to BJT. So you need to know their advantages and their disadvantages. Now these are the transistor. Okay. I believe these are the one that we commonly see, okay, in our lab or in your projects. And of course, these are the small transistor, small power transistor. So for those high power one, like I say, they're always in the module form, in the bricks module form, okay, or in this form, where you can see that, oh, the size, right, and the size of the pencil. So it's quite big, all right. And for the MOSFET, right, again, there are two types, okay, N channel and P channel. And the most commonly used is N channel, okay. So this is just a basic, what we call the constructions, okay, cross section, okay, of the MOSFET. You can notice that there is no physical connection between the gate, okay, and the semiconductor. In between, there is a layer of oxide, okay. There is a layer of oxide. That means there is no current passing through. So it relies on the electric field. That's why it's called field effect transistor, okay, to actually attract this electron that form a bridge so that the current can go through, okay, because it's positive, it will attract the electron, all come here at this point, okay, and form a bridge between the D and the S so that the current can pass through, or else there will be no current pass through between D and S. So that means the higher the voltage I apply at the gate, right? So the higher the electric field, the positive electric field I have. So it will attract more electron or negative, okay, electron, negative charge that will form a wider bridge so that more current can pass through. Because if you have just applied a very low voltage, it will still form a bridge, okay, just like pipe lah, okay, so that the current that can flow through is limited. So this is how the MOSFET, okay, operate. So in terms of circuit, it looks something like that. Okay, so these are the symbols, and these are the control, okay, gate voltage, and this is the voltage that is applied across the D and S, the drain and source. And this graph here is the what we call the transfer characteristic. And you can see that when you apply VGS, right, there's no voltage, you have no current pass through the ID. Okay, I think. Okay, VT is the threshold voltage, okay, of any MOSFET. So if you apply voltage lower than VT, right, there is no current flow through, meaning that the transistor is in the turn off state. Okay, that means the positive you apply here, right, are very low lah. Okay, let's say these are the positive charge. All right. So when you increase, okay, the positive charge, let's say at this point, and you will start to see there are current flowing through already. Okay, meaning that you have more positive charge, you increase. Then it will attract more electron, right? Okay, it will start to attract electron, negative, 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 forming a bridge. So that current will start to flow through. Okay, start to flow through, all right, in this. So as you increase more of the VT, you will see that the current of ID increases. So that means there will be more electron attract here, and it form a wider bridge. Okay, it form a wider bridge so that more current can flow through. Okay, more current can flow through. So this is one of the very important characteristics that you need to know, okay, for your switching device. All right. So up to this point, any questions? Okay. So we move on. All right. Now, in order to understand more about the transistor, okay, we actually measure the transistor in terms of transfer characteristic and output characteristic. Now, transfer characteristic means that, okay, ID versus VGS, like what you all show, just see this now. Okay, ID and VGS, okay. That means is how the gate voltage affect the drain source current at constant VDC. So that is the first characteristic. The second characteristic is the output characteristic is ID versus VDS. Okay, ID versus VDS on how different gate voltage affect the drain current at different VDS. If you look at the graph, it will look something like that. Okay. So this is VDS. Again, this is ID. In many of the textbook, it will show you like that. There will be a graph, straight line usually, and then 2 line, and then 3 line, and then 4 line. Each of the line will represent different VGS, the gate voltage. So it will tell you the higher the gate voltage, right? The higher the ID you can get. Okay. So in many textbooks, this is what you see lah. Okay, in many textbooks, this is what you see. Now, this is academic. Now go back to industry. Okay, so like I say, industry, you get it from the data sheet. They never show linear graph. Okay, you go and flip all the data sheet, you cannot see linear, but you go and flip all the textbook, it's all linear graph. That is where students and industry start to have what we call mismatch lah. Okay, so these are the main mismatch between academic, what you teach or what you learn in university, you go out cannot apply, you blame the university, they never teach you, right? But if you sit down and look back carefully, right, they are actually the same thing. It's just in the different perspective that you thought. One university never teach me this, totally different from the textbook. So textbook's bullshit, right? No, okay? So that is what I'm trying to make you all clear. Okay. Now to model, okay, we already learned how to model diode, right? So now we learn how to model transistor. So in Simulink, okay, yeah, there are, again, a few types of MOSFET, IGBTs and so forth. So now we look at MOSFET. And okay, IRF Z44N, okay, this is one of the very common MOSFET that use. And again, you can see this one is their transfer characteristic. Okay, like I said, they use log graph. Okay, that's why it looks so different. In textbook, it should show something like that just now, right? Okay, but now it shows like that. And the other characteristic, okay, this one more important in a sense that you see, they use x-axis and y-axis also log, is a double log. Okay, log x and log y. This one is only log y, while x is linear. Okay, so you have to see carefully. Oh, this is, the two graphs. So when you want to model, right? Okay, now this is how you're going to model. Okay, please download this from the internet. Okay, I have done this, so you all just later just test it. Okay, so now this will show you how to test, okay, the transfer characteristic. Now this is the transistor you put in, okay, and then we change the gate voltage. Remember, the gate voltage, the higher you get, okay, the better in contact, or the higher the drain current. Okay, so that the other sensor here, we measure the current ID, okay, and this is a VGS. Okay, so again, when you run this, right, okay, or another thing, before that, you need to model this transistor, right? So first of all, you need to look at the data sheet. Now you open the transistor, plots the parameter specific from data sheet. Okay, you can see here. That means I want to model it based on data sheet. Then you look carefully at this RDS. Okay, the RDS turn on. Okay, RDS on, see, is here. Is 17.5 milliohm. Okay, that is RDS. And then your drain current for RDS turn on. Now you see, your RDS turn on, right? Your drain current is 25 amp. Okay, so you need to fill in. And then the gate source voltage, VGS, all right, for RDS is turned on. Again, based on this one, that is 10 volt. That is 10 volt. Okay, this one and this one. And the last one, okay, will be the gate source threshold voltage. This is the tricky part. You see, even the data sheet can't tell you the answer. It tells you 2, minimum, and it tells you max 4. Then what is the typical value? Hit yourself. Of course, that's why you need to have try and error already to make sure you run and compare to the real one until it match. Okay, so what I did is that I get around roughly 3.6. It should be between these two values. The answer is between 2 to 4. But the manufacturer also cannot, because that is the part, okay, of making a transistor very difficult to control exactly the voltage that they want. Okay. All right. So it's a manufacturing process problem. So this one I'm showing here, make sure that you all know how to get the value. All right. Because it will be in the exam. My exam will be, at least there will be one question, I will throw you a data sheet. Okay, and then I ask you, okay, calculate this and what. You don't tell me, sir, what is the value of RDS? It's inside the data sheet. Okay? Okay. So this is important. You must know how to read the data sheet in order to obtain the information that you want, okay, to answer my questions. Now we come to the second part. You see, this is the first part. The second part of the modeling, again, they got main, and the next one is the capacitance. You see, the capacitance got input capacitance. Remember, when there are always a gap like the gate, right? And the semiconductor in between is what? Is an oxide layer. That oxide form a dielectric. So in this case, it will have a very small capacitance in between. Most of the time, we just ignore them, okay? But when you really want to model the transistor, this is the value you need to know. For example, the input capacitance is 1470. So look at the data sheet. It's 1470 picofarad. Okay, it's here already. All right, it's here. And then you have another one, reverse transfer capacitance, 88. See, it's here. Output capacitance, 360. 360 is here. All right. So information are all inside the data sheet. Now, capacitance is important when you are dealing with high frequency switching. If you are dealing with low frequency switching, basically it doesn't really affect your circuit that much. Okay. So, but you are dealing at how high is the frequency. For example, you look at the data sheet. If you are dealing with 1 megahertz and onwards, right? Then you need to model this. Okay. Okay. So after you do this model, in the program, right? The MATLAB program I did. Okay. Okay. So like I said DUT, okay, device under test. You can, I mean, you don't need to open up. I already fill in all the value already. Okay. I already fill in, but in case you want to model other diode. Okay, that is what you need to do lah. So just need to click the blue button. Okay, then we will see. Is it running? Oh, how come? Okay. Different folders. Okay, you have to put inside the right folder in order for it to run. Okay. Okay, I intentionally brought two graphs. One is the linear graph that you all see in the textbook lah. Yeah. Okay. Sorry, That's okay. Okay. Okay, you should have two graphs here. So one is a linear graph, one is a graph that follow the data sheet. Okay. So you can see that this one is from the data sheet. This one is the model. So pretty close. There are some gap here, which the model in MATLAB allow you to model. That is the best I can do lah. I can model at this using this model. That's why every year they will improve the model a little bit until like the diode we can fully model exactly the same like what you show in datasheet already. Okay, so it's the same thing. You can see the characteristic is that when you apply more than 4 volt, okay, then only it will start to turn on. Right? You apply 3 watt, okay, or 3.3, you will not turn on the transistor. Okay, and you apply 5 watt, these are the common one we use for Arduino, right? Output 5 watt, yes, it can turn on, but not fully on. Okay, it's still not fully on, all right? But it's good enough for many applications already because you can see that if 5 watt, right, it almost reached like 20 amp, you can, your circuit can supply up to 20 amps. So these are what we call the output or the transfer characteristic, okay, of a MOSFET, okay, of a MOSFET. All right. Okay, so we move on. Now you can see if you compare to the data sheet, the data sheet show 2 lines. One is at the normal temperature of 25 degrees and one is at the temperature of 175 degrees. So we can see that though the one on the 25 degree, okay, which is this line, all right, which is this line, pretty much, okay, similar, I would say. Okay, of course, it's not exactly, but pretty much similar, especially at the point from 5 volt, okay, to 6 watt, okay, it is overlap. Okay, it's overlap. That's in that this is the range that you matches the data sheet. Now the next one to test is the output characteristic. Okay, again you can download it. Okay, from the MATLAB. Now the difference between the transfer and output is that now the VGS, okay, will change in steps, all right? And then I need to measure the current, okay, and change the VDS. Remember the graph for this one is the change, okay, it's like that, right? The VDS change. ID is here. So let's say if I apply 1 watt here, I will have something like that lah. The VGS is equals to 1 watt. So by running one time, I get only one graph. So I need to change this to, let's say, 2 watt. So I change 2 watt, I run again, I should have this one because the VGS is increased to 2 watt. And so forth lah. So I increase more, you will see more. Okay. So by running this, you will see something like that. Now you look carefully, this is from the data sheet. Huh? You see here? Here show you is the VGS voltage. It starts from 4.5, 5, 5.5, 6, 7, 8, 10, 15. So you should see the line here is 4.5. And the last one, this one, is 15 watt. So meaning that this is 5 watt. This is 5 watt and this is 5.5. And this is how we can create. You can see it's very much close. I won't say exactly close to what we can see in datasheet. Okay, when we plot log, you can see also 4.5, 5, but in different color so you can see much more clearly. Okay, so if we can plot this out and compare to the data sheet, it actually shows us, right? Okay, our model is pretty much, okay, good lah. Okay, not excellent, but still good enough. All right. So right now, okay, so I want you all to download this, just run it, okay, and yeah, using MATLAB so that you will familiar yourself with it. Now here is the MATLAB. You should be able to run this, okay. You will see that it runs a bit longer because it needs to plot multiple lines, okay, of the graph. Okay, so this is how you will get, this is what you will get. Don't worry about, what make this thing happen for clicking, This one I will slowly teach when we go into converter. So the first of this chapter, I just want you all to familiar with Simulink. Download, open, run, make sure it can run, and we do some simple connection of circuit, okay, like the reverse recovery, okay, and slowly we move on to a more complex one. All right, so those online, please do this and screen capture and show me. Physical class also. The problem is that, you see, our class now got 110 students. It's half of the class really doing of this. When I check, because I can actually check how many of you have downloaded. And I look at it, a bit disappointed, in a way that, hey, I do this, I spend time on, It's not like pop, come out one, And you are a guy like just like, never mind. When we don't do, you say don't teach properly. Because sometimes like, okay, let's see. Especially the first one, the diode one, important one. Wow, less than 50 students. There's one still not minus those not my class student to download, you know. Okay, this is MOSFET 3031. Excluding, I mean, you know, this one include whoever on the internet can download. And because I just upload in 2nd of January lah, so I assume that, okay, all 30 is our class. These are all my teaching material. I used to teach power system, protection, so I create all this model. Of course, also including those research project and FYP lah. So you can see I actually created a lot of this, okay, for the teachings so that you all can see things, how it relate to the industry. And all this download, I had no money to collect one. This is all voluntary. So don't think that I'm making money here because this is just for the public. Hey, where is the diode? Okay. Maybe. Diodes here. 48. Okay. Let's see. Okay, good. Got error. Jing En. Wow. Interesting. Okay, just click the two fix. It will create the new variable for you, Jing En. I think the second one, create a new variable. You just click the fix on the second one. Load a file into the, I think this one no need the first one. After that, it should be able to work, Jing En. Make sure it's in the same folder. Jing En, you hear me? Okay, physical class. You all can right? Or cannot? Some problem. Oh, cannot. Why I want you all to download is because I don't know this one, I will ask you all to okay, don't worry, the model is correct. The number is because I have it right a split for all these nine. After this power electron, you cannot. Okay, make sure that you all have to run it, okay, inside the, what we call this MATLAB correct folder lah. You see, when you run MATLAB, okay, so this is your MATLAB interface, huh? So when you download, right, you can see that C user, your name, document, and MATLAB. MATLAB will create a folder here. This is what we call a working folder, okay, for MATLAB. So you have to make sure that you create all small folder here, okay? Okay, like this one. Then you open and run it here. If you run it outside somewhere else, right, MATLAB cannot find, so it will give you errors. Jing En, have you run it already? Okay.
Sir.
Yes.
So while you are waiting for us, right? So I want to ask some question regarding the. Just now you say the transfer characteristic, right? That one the 3.6 for the gate source, right? That one, because in the sheet there, I written minimum 2 to 4, right?
Yeah.
And then the 3.6, how you get it?
Try the error. Every time I put, like, let's say I start with 3 lah. In fact, I start with 3 because I take the average between these two, ma. Then I plot the transfer characteristic. And then, okay, maybe let me show you here. Then you will try to get as close as possible to the one that fit the data, what we call the data sheet result.
One by one.
Yes, one by one.
Also, we have to have one by one until it get
close enough to
matches the most with the.
Yeah, because like I said, even the factory, right, cannot give you the exact one. Because making transistor, let's say they make 1,000, right? They will always have different, not every one of them got identical. Now, let's say I look at this output. Okay, so, okay, let's say, okay, if I put 2 or 4, you see, it off already, right? The blue color is the model. The dot one is the datasheet point one, right? The one that show in the datasheet. You see, if I put 2, it's off, totally off. So cannot. Okay, then say lor. And you look at the characteristics, you see it's not right already lah. Okay, because it will turn on even at 2 volt, you know. That is the minimum they set. So let's say I try 4. I mean, these are the 2 extreme. And I run again. That's why modeling is not just key in just data. Some value you need to do a little bit of fine tune. Now, okay, it somehow cross over lah. So that tell me that, okay, it should be between 3 to 4 already, right?
Yeah.
And then you can see that it go higher lor, and also doesn't make sense. Okay, then I will just like, okay lah, I try just now 2 cannot, 3, 4, then now let's say 3. Then I slowly 3.1, 3.2, or 3.11, 3.12 kind of, you know, of adjust it lah. But I play with only 1 decimal lah. You see, 3 is still on top, but the shape very much close, right? It just shifted. So I know that it's actually between 3 to 4 already. Yeah, this is how we do lah.
Oh, okay, sir.
Okay, so yeah, I think most of you had done it. Okay, so we just move on. Okay, now the next one will be the IGBT. Okay, so previous one was the MOSFET. Okay, we have to do the transfer characteristic and output characteristic, some basic modeling, you know, technique. Okay, so you can use to model the transistor. Now, IGBT combine the advantage of BJT, okay, and the MOSFET. Now remember that MOSFET, okay, have a lower current but higher switching frequency, whereas BJT has a higher current handling capacity, but what we call this a lower frequency capability. So in the old days, right, because of this problem, you cannot simply serial or parallel BJT and MOSFET, okay, because the nature of their operation are different. Current control and the voltage control. So the industry and of course those researchers have to think out of the way. So they end up with combining these 2 together to make 1 transistor called insulated gate. Oh, sorry, a typo here. There's a E. Bipolar transistor. So by combining this together means that they get this BJT and MOSFET to get married. Okay, then they have a children. that will have these two characteristics. So IGBT become a voltage control gate, can handling high frequency. And then the D and S, right, it become collector and emitter that can handle high current. So the combination of this is the result, okay, as IGBT. Similarly, IGBT also have the transfer characteristic and the output characteristic. The only difference is that, okay, instead of ID, drain current, it become IC lah, because the collector, the drain and source become collector and emitter. The gate, right? It's just like the gate side, they use the MOSFET, but what we call the collector and the emitter side, they use BJT. That is how they combine, okay, and make a new types of transistor. So similarly, okay, yeah, you can actually use the same model I created just now. What you need to do is that you need to change to IGBT, because previously you can see that here is MOSFET, right? The symbol is MOSFET. And then you can see that this IGBT. You see IGBT, the gate instead of base. But the output side here, okay, become collector and emitter. All right, so in terms of data sheet, okay, so again, you can actually do the setting, okay, based on the data sheet here. All right, then you just need to find out what is the gate emitter threshold voltage, okay. Then you can see here is the gate threshold voltage. Now the good thing is that this one, they can give you 3.5 minimum, maximum 5.5, they give you the typical. So easy, straight away you type in typical 4.5. And then you look at the collector emitter saturation voltage, VCE, okay, 2.5, 2.1. Then you can look at here, okay, the collector emitter voltage. Now you got three values here, 2.1, 2.5, 2.6. So which one to use? Of course, you look at the condition. The condition is 25 degrees, that is the typical. So we use 2.1, but it gives you max 2.5, meaning that there are chances that there will be value in between 2.1 to 2.5. Okay, when you do the model, all right. And then, yeah, the rest okay, can be all found here. For example, like this continuous collector current, okay. So 12 volt, 12 volt, okay, emitter gate voltage 15 watt, and so forth. So it's a matter of really understand all the parameter and get it from the data sheet, okay. So this one, I don't do the simulation already, because it's the same, I will say now, right? Okay, so now, like I explained just now, okay, the combination of both. Now you can see that this is the transistor, okay, the transistor symbol, right? Collector, emitter, and base, all right? So this will be a typical, transfer characteristic, textbook based, so it's linear graph. So it just gives you some rough idea, okay, it can operate like up to 20 kilohertz, current it can handle like 600, okay, and then these are the MOSFET, okay, MOSFET can handle, okay, higher switching frequency, but lower current, you can see 600 to 100, like, 20, okay, so that's the difference. So now when you combine both together, right, it will have higher than BJT, but still lower than MOSFET. Okay, so in between, okay, then it will have very much higher current handling capacity. So you can see this part here is a MOSFET. Okay, this one is the MOSFET. And this part, okay, is the BJT. Okay, so these three slides, right, you will start to see it much more clearly. All right. Okay, so that's all for transistor. All right. Oh, not all. Still got two parts. Sorry. Okay. This one, in order to control or drive IGBT or MOSFET, you need a device or core driver. Now you only need this when you want to make prototype. Okay, very important, because if you don't use this driver, a lot of your circuit will not work properly. So the driver play a very important role to ensure that your IGBT or MOSFET are fully operation or fully turned on, not just turned on partially, that you will never get the full current capacity, okay, of the MOSFET. Now to do that, okay, you need what we call a gate driver chip. Typical one is IR21XX, okay, it can be 210102 and so forth lah. Okay, so instead of directly connecting the output, right, of, let's say this is your Arduino output, you don't connect it straight to this MOSFET or IGBT. You need a driver circuit like this one to connect. Now, I have to stress that it also depends on application. Some application is okay. You can direct connect Arduino to it. Okay, some cannot. Really depend on the converter you are designing. All right. So this is just on your knowledge, because yeah, if your assignment does not need to make prototype, then no issue lah. But if you want to make prototype or any hardware, okay, this is something that you need to know. Okay. Now the next one is transistor switching loss. Okay. Now we know that transistor is a switching device. We turn on and turn off, right? Okay, at a certain frequency. Now, every time when we do this switching, turn off and turn off, turn on and off, we will have this issue called switching loss. Okay, why switching loss? Okay, if you look carefully, when you turn on from, like say, VDS on to off, and then on again, right? So you will notice that, right? There is always, it needs time to from low and go to high. It does not go immediately like a square wave. Okay, when you zoom in, right, you will see, okay, it takes time. So there is always something like, turn on time and turn off time. So during this section, okay, during this session, the transition, okay, it will cause energy losses. So this is what we call it transistor switching loss. So what does it imply? Okay, it implies that the higher the frequency you use, the more switching loss you get. So, when you design, you have to take balance, no? The higher the frequency you use, the smaller the component you can get, right? Why our charger becomes smaller nowadays? Because they operate at very high frequency already, up to like 150 kilohertz. Okay, but the problem is that, okay, high frequency lead to high frequency loss. So you have to balance of which one is important in your application. Is it size does matter? Size matter, you need to use high frequency. And is your power of your converter, of course, higher power, right? Let's say 1% loss is a lot, right? Compared to, let's say it's 1000 watt of power. 1% loss of 1000 is a lot. But if you're like our charger, 33 watt or 35 watt, now they call fast charger, 1% loss, nothing, right? So like I said, this is part of the design thinking that you need to think, okay? Which one, okay, you need to consider first. Now, you can actually simulate this, right? In this Simulink, okay? You actually can simulate what the data sheet show. You can see that it takes some time for the turn on and off. Will look something like that. So we need to take care of this. Okay. And then this is the switching waveform that you need to know. Okay. We need to know a few terms. The first is turn on delay time. The moment you apply like 5 watt to the gate, right? It does not turn on immediately. It will take some time before it starts to increase. This is called turn on delay time. Okay, all these switching device have a turn on delay time. It does not turn on immediately because it's so fast we doesn't feel it only. When you use scope or whatever to see, right, you can see, oh, it really take, a few nanoseconds before it really start turn on. And then after that, it will have what we call a rise time. Rise time means that from 0 to the full turn on time lah. So it's called rise time. So again, here it takes some time. And of course, when it is already turned on, we call it on time. It on time again, when you turn off, right, it does not turn off immediately. Okay, so we have a turn off delay time. At this point, I already turned off, but it's still on for some time now. So it's called delay. Okay, and then it will have this what we call fall time. So from the top, fall until 0. And then lastly is the off time. So you need to remember all this. Turn on, delay time, rise time, on time, turn off, delay time, fall time, off time. Okay, so all this information, right, you can actually find it in the data sheet. Okay, all this information are given in the data sheet. Okay, these are the data sheet. You see, when we turn on delay time, so it's inside the data sheet already. That's mean when you buy the transistor, the vendor tell you, I got a turn on delay time. Don't blame me if your converter doesn't work properly. I mean, you need to take this into consideration, right? You see, but it's very fast, nanosecond. All right, but don't underestimate this nanosecond. All right, later I will show you after you calculate, you find that, wow, a lot of power just lost because of this. So they got turn on delay time. Remember the rise time. Okay, how it go up. Okay, like in the slide here lah. The rise time from 0 to the to the turn on voltage or current. So it takes some time. You see, it takes longer. 60 nanosecond. And it also got the turn off delay time. You see, the on and the off delay time different is not the same. Okay. Now you will notice why the turn off take longer. Remember field effect transistor ma? The moment you turn on or off, right? The field effect and the charge still remain there. It does not disappear immediately. It is still there. Okay, so current still conduct, just like the or your reverse recovery. Okay, so it takes longer time to disperse all the electron. Okay, so that current won't conduct. And of course, they are fall time. You see, the rise and fall time are different. Now you will see that, oh, rise time is longer, fall time faster, because after the turn off delay, all the electron nearby the gate channel there is all dispersed already. Okay, so it fall down pretty much faster. Okay, compare to the rise time lah. Okay, so it fall down faster, but it rise take longer time. Again, same theory. When you have attracting the electron come in, right, it takes time to build up the bridge for the current. So it takes times to rise. All right. So there is always a reason. So don't assume, oh, I turn on 1 second, I turn off also standard 1 second. No such thing. And some more, every different transistor, okay, like this one, okay, I'm using for this example is IRF 44, right? So if we look at the other one, commonly used one, this one, IRF 540. Okay, this one is another very common one. All right, you can see the turn off time, turn on faster, you know. Now, turn on delay 11, rise time 35. You compare to this one. Okay, you see, the rise time, this is take double the time. Means there more losses. So that's why same circuit, everything same, different transistor, you get different outcome. So you have to know lah. Of course, this one got advantage. You see, the turn on resistance is 17.5 milliohm. Okay, and current can handle up to 49 amp. But you use this one, you may have less switching losses, but your turn on resistance is higher. So meaning that your transistor get hotter, and current a little bit lower, but voltage higher. So you have to balance lah. Wow, which one to use? You know, it depends on application or which one your design comes in lah. Your design specs comes in. All right. So transistor playing a very important role in all the 4 converters. All right. Okay. All right. Wow, almost 9:30 already. Voila. Okay, I think cannot already because the one coming is is very lengthy lah. I have to explain one by one. You know, I also explain. You see, at this point we talk about this already. Now the next one I have to explain. I give you example, okay, of one of the data sheet, and then I have to explain one by one how to calculate the losses, okay, and how to find all this information. And we do a little bit of simple simulation to see the losses. Okay, so I think we stop here for today. Any questions?
No, sir.
Okay. Okay, so if no question, then we will end the class today because we need to leave the classroom already.